Thank you very much, Stefano, for joining us and for agreeing to give a talk, and I will turn things over to you.
Hi, thank you, Chris. Good morning or good afternoon or maybe good night, and welcome to my talk. So this talk is about energy dissipation during seismic slip, during experiments that were done on calcite-bearing rocks, coupled with temperature measurements with an innovative method. And it's a collaborative work, in fact, between INGB and the University of Madrid, University of Padua, in the framework of ERC-FEAR activation, fault activation earthquake rupture project. And first of all, let me thank my co-authors, this big group from Madrid that helped us mainly in basically tailoring their measuring technique to our experimental setup. Then Giulio from University of Padova, and the team from INGB in Rome with Chiara, Massimo, and Elena. So this work has been published partly and in 2021 in GRL, and this paper was well accepted from the community, and they decided to write a blog about it as a Nature Highlights. And but most of the work is unpublished, and it will be published soon in this publication that will be submitted to JGR Solid Earth. So let's start with the seismic cycle. So the seismic cycle spans a broad range of time and spatial scales. So we will start in the interseismic to pre-seismic stage that lasts a number of years, 2,000 years. And you see that on a fault, the shear stress is slowly increasing up to this value, which is normally called tau zero, and marks the beginning of the ecoseismic stage. So in the ecoseismic stage, the shear stress abruptly evolves in a matter of seconds or milliseconds from its initial value tau zero to the peak value, and then decreases sharply down to a minimum value in the so-called dynamic weakening substage of the ecoseismic stage. And then the slip cycle starts again with the post-seismic. So if we zoom deep into a fault zone, in this case it's just an example of a normal fault, we go into here, we can see that actually in a matter of, and this is just a picture, so a snapshot during a propagating rupture. The rupture is staying here and is being modeled with the dynamic numerical models from Chiara, Cornelio. And we can see that during this picture, we take the rupture front, we can see that in a few meters just around it, there are very abrupt anomalies or in shear stress, which are corresponding with anomalies in slip velocity, in slip rate, so the relative slip velocity between the two moving blocks. And the value of slip rates locally can achieve 1 to 10 meters per second. In this case, it's just 3 meters per second, but it's an average of 1 usually accepted for the seismic slip stage. And if we zoom further inside here, we can see that especially the rupture front evolves from the tau zero to the tau peak. The tip of the rupture front sits here, according to this model that comes from Rice 1980. And then just behind the rupture front are the dynamic weakening, which is marked by this sharp decrease of shear stress. And during the dynamic weakening, we see how slip rate is accelerating abruptly, and temperature is slightly increasing and keep on increasing during the entire seismic slip. At this stage, we don't know if really temperature is the main driver of the dynamic weakening, but we still see that there is a correlation between seismic slip and temperature increase and slip rate increase. If we take one single point on this on that simulated fault plane, we can see that its slip history evolves with slip in terms of shear stress from the 3 tau zero, tau peak, and tau r values. And this representation evolution of shear stress is called constitutive law. And constitutive law has been used since the 70s to model seismic ruptures, and they define shear stress as a function of one or more observables. Starting in the 70s, the slip-dependent laws were born from in relation to fracture mechanics. And then in the next years, thanks to contributions from the lab, the constitutive laws evolved and got more and more complex towards, for example, the slip rate and state friction laws, or the slip rate and state coupled with the enhanced weakening with high slip rates. And even more recently, there were attempts to add more physical content to these constitutive laws. For example, with empirical laws mainly focused on landslide collapses, in which it was introduced a dependency of shear stress on temperature and slip rate together, or the same, but in addition to that, with the consideration of physical processes that occur when fault accelerates to seismic slip rates and temperature developed by frictional heating. For example, the paper from Rice with flash heating and thermal pressurization, or the papers from of Nielsen with frictional melting and thermal decomposition and flash heating. But still, it's not really clear if and how temperature is actually driving dynamic weakening. And this question is important. So does temperature drive dynamic weakening? Because we really need to know this to define physics-based constitutive laws that effectively represent seismic slip. And we already have a lot of evidences, more or less strong, from previous studies. And these evidences depend on the rock type. For example, in granite rocks, it's quite clear that temperature is somehow driving dynamic weakening because of the development of frictional melts, also known as pseudotachylites. But in clays and carbonates, the picture is more blurred. We don't really know if thermal decomposition products that have been documented are actually due to an effect of temperature in driving dynamic weakening. But if we start from pseudotachylites, ever since the 1970s, first with the theoretical work and then with actual field work, it was shown that these rocks really occur in nature and they can be associated to seismic slip. And this is an example of a more recent work of very well-formed pseudotachylite rocks. This is one of secondary faults in a more complex fault zone in the Adamello Massif from the Alps. And we can see this very black, this black material, which is basically, it looks like a basalt on the field. It's actually a molten rock due to frictional processes. And we can see these injection features that that branch from the main fault or principal slip zone. Together with field evidences of pseudotachylites due to seismic slip, even since the 1990s, there's been a growing body of experimental evidence, in particular with high slip rotary shear experiments that actually rocks can melt during laboratory experiments. This is the first evidence, one of the first evidences from Spray, and further evidence from Tsutsumi and Shimamoto, in which we could see that with increasing slip rate, these are velocity steps. So with increasing slip rate here, we have the development of a sharp increase of shear stress followed by a sharp decrease, so of dynamic weakening. And then on further work from Di Toro, we've seen that again, with seismic slip rates in the order of meters per second, we have a decrease of shear stress. And pictures on the post-mortem experiment show the development of this coating, this molten rock that can weld actually the experimental samples together. I have a video here of an experiment run in Shiva, and this is one typical example of a high slip experiment. Here on the left, we can see our samples, which are captured with a high-speed camera. On the left, we have a sample which will be rotating towards us, and on the right, we have a stationary sample. In the middle, we have a localization surface between two rock samples made of gabbro. And we've seen that with the progressing of the rotations, on the same time, the shear stress is remaining high. So this is a real-time measurement of shear stress. We start seeing some bright spots due to melting of asperities or formation of small patches of melt. And then at the same point here, we see that when the layer of melt is continuous, the shear stress decreases. So we really have a direct evidence of dynamic weakening due to melting of rocks. And this is just half a second, so it's a really quick process happening. Okay. But still we missed the evidences about temperature. So in recent work, there's been attempts in correlating also the dynamic weakening with the temperature increase with direct and continuous measurements of temperature, in this case from NODA with the infrared thermometer. We really could see that how in gabbro rocks, the decrease of shear stress occurred with an increase of temperature, in this case in the order of 400 degrees Celsius. And in this other case from Wu, a very recent paper with thermocouples, they could see that with the corresponding with dynamic weakening, the temperatures was increasing, and they could really analyze the frictional melts after the experiments to see also how the properties of the melt were evolving. So more on this topic about from stick slip experiments. So it's a very classic experiment that has been used since the 60s to basically as a lab analog of earthquakes as frictional instabilities. We see this kind of sawtooth behavior is due to several consecutive stress drops. So in each of these, there is a little dynamic weakening stage. And this is just an example of stick slip experiments that were done in Aubry recently, in which in correspondence of each dynamic stress drop, there was a measurement of temperature that was inverted from a thermocouple measurement a few millimeters away from the slip zone. And this temperature anomaly was also correlated with a thermal marker due, in this case, was carbonization thermal marker. So after the experiment, so before the experiment, the surface of the sample was coated with amorphous carbon, and after the experiment, they managed to analyze by knowing the kinetics, direction kinetics of carbonization reaction, how was and where and how high the temperature was in several spots on this contact surface. And we see that temperatures exceeded 1,000 degrees up to almost 1800 Celsius in the red spots. Whereas if you move to calcite and clays, the evidence, the natural evidence of seismic slip and related temperature rise were more scarce. Recent work from Collettini has shown that actually calcite behaves slightly different, and clays as well. They tend to, when associated to seismic slip, they tend to decompose. So their crystal lattice is basically degrading. And as you see from the development of this porosity here, on this area of the crystal, if you go under TEM then and you slice this crystal, you can see that the crystalline lattice is basically disappearing in many parts. For example, here it marks a boundary between a crystallized part and an area with a loss of crystallinity or partial loss of crystallinity. And the same happens in clays. So basically in this case, temperature is damaging the crystal lattice. And further high slip experiments in a great number of materials, like from this case of Vitoro and et al. 2011 paper, has shown that in many materials, decomposition was associated to the dynamic stress, to the dynamic weakening, so the decrease of shear stress. And it was the case for gypsum, anhydrite, dolomite, clay, serpentinite, and marble. So really a great number of possible fault materials are interested by this. And in the case, in particular case of carbonate-bearing rocks, thanks to high slip and stick slip experiments and the analysis of microstructures after the experiment, it was really possible to track the advancement and the type of the composition processes involved. In the case of Spagnuolo 2015, basically the calcite-rich marble was on the shearing surface was amorphizing, so carbonate calcium was transforming into amorphous carbon. And in the case of gouges, in dolomite gouges. The Paola has shown how the gouge was evolving from an initial state, coarse-grained gouge, fault gouge, to a very fine-grained dolomite gouge. And locally, the grains were losing crystallinity again. So we clearly see how crystal lattices were basically disappearing with the progress of strain and temperature increase. Recent work from the Paola and from Pozzi has shown instead the importance inside these very localized areas of nanograins. So extreme grain size reduction coupled with evidences of high temperatures due to superplasticity. As you can see here from this peculiar swap, this kind of a very peculiar microstructure that can be related to this process. And similarly, in stick slip experiment, Pasleg has shown the widespread presence of nanograins and occasionally of this kind of filament structures that can be representative of local melting of grains. And on top of this, even from XRD measurements, before and after the experiments, you could see how the peak of calcite here in the starting material was disappearing in favor of lime and portlandite after the experiments. So all of these are evidences on how thermal decomposition and extreme grain size reduction occur in carbonate-bearing rocks associated to temperature increase. But still, the smoking gun, we don't really have a smoking gun. In fact, whenever a direct temperature measurement was tried in this type of rocks, ended up with some sort of contradictory message. In fact, in this case from Han, 2007-2010, the infrared thermometer measurements show how temperature was either decreasing or increasing when shear stress was decreasing. This is a very pioneering work, but still I really have the feeling that we needed to investigate further this topic. So in fact, does temperature drive dynamic weakening? Yes, so the evidences are quite strong for granitite rocks, but they are a bit weaker perhaps for clays and carbonates. And for sure, temperature is increasing during seismic slip, but it's still not really clear if it's driving dynamic weakening. In particular, in carbonate-bearing rocks, earthquakes are widespread, especially in central Italy. In this case, we have the example from L'Aquila sequence in 2009, but there is also the more recent sequence, 2016 and 17. In a bit northern with respect to this area in this image. But there are also examples in Greece in the Aegean earthquake and in China in the Wenchuan earthquake, especially in the northern part of the Yingxiu-Beichuan fault zone, fault system. And these earthquakes are quite peculiar because they're shallow, they nucleate a shallow depth with respect to other earthquakes. And then we want to investigate temperature and understand how temperature is evolving during seismic faulting, because this is reflected in the energy balance during seismic faulting. In fact, if we know the energy balance and the temperature increase, we could really invert for the shear stress during earthquake ruptures themselves. And we can do so by combining laboratory experiments in order to constrain the energy budget with boreal measurements or temperature proxies to constrain the temperature evolution. If we start with this energy balance formulation from Lambert and Lapusta, we can draw an equation in which we can write an equation in which on the left hand we have the change in strain energy per unit area that is equal to the sum of the frictional work per unit area and radiated energy per unit area. We can move from this energy balance by converting the change in strain energy to this term, which is called energy-based shear stress, by means of the static stress drop and the average slip during the rupture. We can convert the frictional work to the dissipation-based shear stress by dividing the frictional work to the area times the average slip. And we can convert the radiated energy to the apparent stress by dividing the radiated energy by the area and the average slip. So we basically end up with this from the energy balance to the balance of shear stresses during seismic slip. So the frictional work is this gray shaded area, and the radiated energy is this blue area. Whereas this hashed area is the change in strain energy. If we move further on, we can decompose the energy-based shear stress as the initial shear stress, which is really the unknown part, that the one we want to estimate, and as a function of the energy-based shear stress and the half of the static stress drop. Whereas the dissipation-based shear stress as two main contributions, one heat contribution and one non-heat contribution. So we end up by replacing in this equation and obtain the absolute level of shear stress as a contribution of at least 4 elements. 2 are based on dissipation and can be estimated with laboratory experiments. 1 comes from the radiated energy and 1 comes from the static stress drop. Moreover, we know from laboratory experiments that this term can be ignored. And so we can simplify the energy budget like this. And temperature evolution is coming directly from the heat part. And the heat part is used to calculate temperature by means of this equation. So the evolution of temperature is equal to the diffusion term plus this heat source term, which includes the beta coefficient and the product between the shear stress on the fault, the slip rate, and the degree of localization across the fault. And beta can be equal to 1, so that the entire dissipation of energy is converted into heat, and we are happy about it because it simplifies the energy budget. But there are several cases in which this term beta can be between 0 and 1, can be smaller than 1, and so we need to include other contributions in the estimate of shear stress. And this is complicating our energy balance a little bit. If we move to carbonate-bearing rocks, this is clearly the case because thermal decomposition and comminution can really alter the energy balance equation. And so for sure, we need to include this term in our equation, and we will need also to constrain this energy balance with laboratory experiments, because it's probably the only way that we can use to constrain this. In fact, if we want to summarize this part, the temperature is increasing during seismic slip. We have a wide number of evidences. At the same time, high slip and steep slip experiments both show that shear stress is decreasing, so the dynamic weakening is associated to fast slip rates. And in some cases, we can also have a direct evidence that temperature is increasing in relation and can be related to dynamic weakening. At the same time, carbonate-bearing rocks host seismicity in many areas around the world. In this case, kind of rocks is not clear if temperature is driving dynamic weakening. And we know that the energy budget is affected by the reactions that undergo in these rocks. And therefore, also the shear stress estimates are affected by the energy budget. So to address these questions, we run a series of seismic slip rate experiments using rotary shear machines capable to impose high slip and slip rate in our samples. And the faults were represented by either rock and fault gouges. And together with the experiments, we ran temperature measurements with the two-color pyrometer and temperature models. And by comparing the measurements and the models, we managed to discuss the energy budget during seismic slip. And in the next slides, I'll show you how dynamic weakening is actually driven by temperature. And this is important to define constitutive laws for dynamic rupture propagation. And that energy budget during seismic slip might be actually more complex than expected. And this is important whenever we want to calculate the absolute level of shear stress associated to natural earthquakes. To do the rotary shear high slip experiments, we use the Shiva, slow to high velocity apparatus, and Shiva is a rotary shear machine. We normally divide it in two parts. So there is a rotary side on the left. This is a rotational shaft connected to this large motor and to this small motor. On the right side, there is an axial piston that moves in this direction and is controlled by this axial piston, electromechanical cylinder, and the sample sits in the middle. So with this part, we apply the normal stress towards the left, and with this part, we apply the shear, we apply slip rates. And so there is one sample here connected to the left part, which is spinning, and one sample connected to the right part, which is actually moving in this direction, and transferring the normal stress to the other sample. And the objective here is to apply seismic slip rates and to measure the shear stress evolution. If we go in this in the sample area, I'll show you directly one of the experiments run in marble samples. In this case, it was a rock sample, and we see that during this, should be like 4 seconds and a half, we have 20 meters of slip at 6 meters per second, the maximum velocity. And we really see that the sample is undergoing some reactions, especially if we look at the distribution of this luminescence that occurs during frictional heating. In fact, we could see some local banding and other effects, and the sample is actually burning due to the frictional heating. And during this experiment, in fact, we managed to sample temperature from the shearing surface. This is a cross section for the rock type experiments. We see these two lines are representing two optical fibers that were going inside directly on this sample surface here. This is the contact surface between the two twin samples. And in the case of rocks, we run experiments at 20 MPa under dry conditions with a boxcar slip rate function, which has this kind of shape. In the case of gouges, thanks to a sample holder, we managed to confine a 3 millimeter thick gauge layer in this part of the sample holder, which was kept in place basically thanks to these Teflon ring confinements. And this part is sitting on the left here, on the rotational side. At the same time, the stationary side here at the hole, the optical fiber ending just on the surface here and glued to this sample holder, which is represented by these two lines. And we ran several experiments at 20 and 30 MPa on this 3 millimeter thick gouge with both boxcar and the Joffe slip rate function. The Joffe function, as proposed in Tinti, are one of the best ways to represent seismic slip during earthquake rupture propagation. And this is the instrument we use to acquire infrared radiation from the sample, which is black body infrared radiation produced during frictional heating and fast shearing on this surface. And it's called two-color pyrometer. It's called two-color because basically the infrared radiation is split into two channels. In this case, we even use two fibers together with slightly different optical properties to be able to extend or to try to extend the measuring range and try to also to see the role of type of fiber in the measurement itself. And the idea is basically to collect infrared from the surface and to convert it to temperature. But to do so, we need to calibrate our material in a furnace and to establish the relationship between the spectral radiance emitted in these two wavelengths, one per each channel, and the temperature itself. So we can invert for temperature during our experiments. It's a really unique instrument. This is a property of Madrid University and was tailored to our experiments thanks to the team from Madrid. And it's really unique because you can go at very high sampling rates. You can sample radiation from very small spots. And the temperature range is wide, between 400 and 1300 Celsius. Together with the temperature measurement, we wanted to do also temperature numerical model to compare the two and establish and try to constrain the energy balance. So starting from Sulem and Nielsen work, I developed this numerical model for temperature diffusion and the temperature production by frictional heating, which comes from the beta times tau times V and delta, which is this part of the equation, and corrected by the heat sink, because we know that the thermal decomposition of calcite is actually an endothermal reaction, and so it's subtracting heat to our frictional heat. In the frictional heat term, shear stress and velocity come directly from the experiments, are really directly measured during the experiments, and the Dirac delta was used as a maximum degree of localization in our tests. Calcite decarbonation was implemented as Sulem and Nielsen with a slight change, because I included also this reaction rate term, which is depending on temperature, of course, but depends also on time. So this allows us to really model the transient effect of the heat sink as well. If we move to results here, we can see one of the rock friction experiments. In the rock friction experiments, basically, we have this very abrupt increase of slip velocity, slip rate up to this plateau value. And at the same time, we can measure the shear stress, in this case, to compare experiments with different normal stress. We're actually discussing friction as the ratio between shear stress and normal stress. So we can see that during the acceleration stage, for example, here we have a decrease of friction. There are more stages inside this experiment, because there is a really stage one at the very beginning when the shear stress is increasing to the peak value. Then we have the second stage, which is the dynamic weakening proper, which is only a part of the entire seismic slip experiment. And then we have a dynamic stage in which friction is constant with slip velocity, and we have a recovery of friction during the deceleration stage in stage 4. Shortening is basically not changing. In fact, in bare rock is very, as we've seen in the video before, the rock are not really compacting. This is probably due to the fact that friction is so low that you don't need really to deform the rocks outside the slipping zone. During this experiment, you have the temperature measurements, and we see that just at the end of a dynamic weakening stage 2, we have the achievement of a plateau. So temperature stays constant between the end of stage 2 and the end of the experiment. And it stays constant at around 1000 degrees. If we compare then the temperature, the measurements of temperature in red and magenta with the temperature model, we first have to keep in mind that the model is actually outputting temperature in 2 points. So the point in the middle where the maximum of, so where the rock contact is, and represented by the black curve, and the temperature more or less 100 micron away. So this number is a measure of basically the spatial uncertainty in positioning of the fiber. We see that the light gray curve output in correspondence of the fiber tip is also achieving a plateau, but it's a bit slower than the actual measurements. It means that it achieves the plateau a bit later, and there is a stage here in which the temperature measurements are higher than the modeled ones, and a stage in which here on the temperature, the model temperature is more similar to the measured ones, and they achieve a similar value in the temperature plateau. Then, if we move to the gauge experiments, again, we see similar sub-stages during the seismic slip experiment, the initial slip strengthening stage and a dynamic weakening stage 2, and then a stage in which friction is more or less constant, and a stage in which friction recovers. And this is true independently of the slip rate function. So here is a boxcar on the left, and on the right is a Joffe function. We see that the Joffe is characterized by a very fast acceleration at the beginning and a very slow deceleration in the end. Again, here we have a slip strengthening stage 1 and a dynamic weakening stage 2, which is sharper than in the previous case. And stage in which friction is constant, stage 3, and then a recovery of friction during stage 4, during the deceleration stage. Here, shortening is evolving in a more significant way because there have a lot of processes of strain localization happening, unlike in bare rock surfaces. But still, the temperature measurements show that we achieve a plateau, even if at lower temperatures. And this is typically happening after the dynamic weakening. So it's a bit delayed with respect to what happens in rocks. If we compare the numerical model results, so the light gray curve is basically the output of the model in correspondence of the fiber tips. So on the boundary between the gauge and the metal holder, the model temperature is lower than the measured temperature at the very beginning during dynamic weakening, or is not really measurable, as in this case, in which probably frictional power wasn't high enough. And later on, the modeled temperature is actually higher than what we directly measure during the experiments. So let's try to discuss our results. The first point I want to make is what's happening during dynamic weakening. So during dynamic weakening, this is only stage 2 in rocks and in fault gouge with the Joffe slip rate function. You can really see how shear stress is decreasing with increasing slip. But it's not just an effect of slip, because it's decreasing simultaneously with the slip rate and with temperature as well. So a combination of temperature and velocity are really driving the decrease of shear stress. And the same happens, in fact, in fault gouge, even if temperature is a bit further away from the center of the slip zone, we can see a similar effect. Shear stress is decreasing with slip due to both the increase of velocity and the increase of temperature. And it's a strongly nonlinear effect, in fact, due to the combination of velocity and temperature. This direct relationship between the decrease of shear stress and temperature was only possible to be done thanks to a continuous temperature measurement. And so this is really what I think a really strong point about having a continuous temperature measurement during the experiments. If we go then observing in detail what's happening in dynamic weakening during in rock experiments, during stage 2 in rock experiments, we can see that the modeled temperature was actually lower than the measured temperature. And what's happening here is probably that the measured temperatures are an intermediate value, in black here, are an intermediate value between the flash temperatures. Here we have several estimates of flash temperatures with an increase of real area of contact. And what are the bulk temperatures obtained with numerical models with our starting hypothesis as discussed before? So probably at the very beginning of the experiment, we are not really seeing single asperities temperature, but possibly a group of asperities, the temperature coming from actually a group of asperities. So we are kind of in a gray zone between asperity scale, flash temperatures and flash weakening, and bulk temperatures and weakening processes. And possibly with increasing slip, we are at this sort of envelope across that is actually representative of an increase, slight increase of area of contact. Could be also explaining this. Then if we move further and we analyze the occurrence of the temperature plateau, we've seen that the temperature plateau is actually a direct reflection of the fact that we have a heat sink going on during shearing. In fact, here I show the moderate temperatures in red and purple compared to the temperatures calculated without heat sinks, so from numerical models without including heat sinks. And we see that in models, when we ignore the heat sink, the temperature is really skyrocketing, especially in rock surfaces, but partly also in gauge experiments. Then, if we move to the gauges, we've seen that there was an important discrepancy between the the temperatures obtained with numerical models and the measured temperatures. And not all of this discrepancy can be explained by the presence of or absence of heat sink. Here again is the case in which there is no heat sink, and so the discrepancy would be even higher with respect between the modeled and the measured temperatures. If we include a heat sink, there is still an important discrepancy, especially here after the dynamic weakening stage. But if we start changing the parameters behind the model, for example, by decreasing the activation energy of the carbonation reaction, or by decreasing the amount of frictional work converted into heat, we can see that the two curves start to be more similar, even if I would say that at the very beginning they are not matching. Towards the end, after dynamic weakening, during dynamic slip and dynamic friction values, they become more and more similar. Why decreasing the activation energy? Because it has been proposed that due to amorphization and grain size reduction, due to mechanochemical effects, it could be the case that activation energy is actually decreasing down to 80, 90% or 75% of the actual activation energy of the carbonation reaction. There are a number of papers that come from the mechanochemistry community that address this issue. And whereas in this case, beta means equals to 0.6 means that the remaining of frictional work can be expended to can be spent to reduce grain size of the gouge or increase or partially amorphize the crystal lattice of the calcite grains, other than really transforming into a temperature increase. And finally, as a final remark, another important issue that came up was that at the end of the experiment, so this marks the final part of the experiment. In a case of a bare rock experiment, we've seen that the temperature is staying high for longer than expected, and to higher values of temperatures with respect to numerical models. So this means that in part, diffusivity is a bit different in real life compared to models, but also that the amount of temperature anomaly stays in our shearing surface for longer times, and could lead to this sort of grain growth processes, meaning that basically due to temperature increase and there's this sort of grain growth that similar that as happens in myelonites. I think it's called, this process has two important implications. And one is that probably it could lead to a lower survivability of the microstructures in equilibrium with seismic slip. It means that basically this kind of microstructures being cooked for quite a long time, and this cooking can obliterate what can be referred to the seismic microstructure. And another important thing is that in the immediate, right after the experiment, so right after a seismic slip, in the immediate the beginning of the enter-seismic stage, it could be that post-seismic thermal healing can be more important than previously thought, and that a reference to the recent work of Bedford. So to summarize with the implications here, we've seen how calcite-bearing rocks are widespread across the depth and can host seismic ruptures in many places worldwide, among which Italy, Greece, and China. But despite their occurrence, there is very little little is known about the direct effect of temperature on dynamic weakening and on the energy budget, on how energy budget is constrained. Thanks to high slip rotary shear experiments, numerical models, and new temperature measurement, we managed to show how in rock faults the dynamic weakening was controlled by slip rate and temperature increase, and how the carbonation heat sinks were active during dynamic weakening, and a possible mixed asperity scale and bulk heating during the deformation. Whereas in gouges, dynamic weakening was controlled also by slip rate and temperature increase, but the carbonation heat sinks were active slightly after dynamic weakening. And in both cases, the early post-seismic healing could be promoted by the permanence of higher temperatures than expected after slip. In terms of energy budget, we've seen how in rock faults, the mechanical energy was dissipated as heat and the carbonation heat sink. And the same happens in gauge faults, but we needed also to include non-heat processes, such as by means of making more efficient the decarbonation reaction by decreasing the activation energy, including in this way the mechanochemical effect, or by decreasing the amount of frictional work converted into temperature. But actually, any combination of the two would occur, and we cannot really districate the contribution of each. Mineral composition and force structure were shown then to affect energy budget and also the estimates of shear stress. In fact, in both cases, we couldn't really assume that the dissipation-based shear stress was equal to the dissipation-based as shear stress only as heat because of the carbonation heat sink. And moreover, in gauge field faults, we need to include the further terms of dissipated energy as the non-heat terms in any combination with a decrease of activation energy, so an increase of effectiveness of the decarbonation heat sink. So in the end, the original simplified energy balance budget on the left is actually, at least in carbonates, something more similar to the right, to the one on the right here. And so we can really say that there is an expected complexity even in the energy budget and also on the estimates of the absolute levels of shear stress that derive from this energy budget. And with this, I really want to thank you for the attention, and I'm open to answer to questions, any question you might have.
Stefano, thank you very much. I'll invite people to join me in thanking Stefano, turning off your microphone or one way or another. Yeah, a lot of interesting things to think about. So please, you can use the reaction button at the bottom of your screen to raise your hand. That'll put us in some order, and we can begin a discussion. They'll invite yes, everyone, but especially early career people to chime in with a question or a discussion point or something. And while people are thinking of their question, I will ask my first question. And that is, you specifically and really very carefully told us about the difference between slip velocity and temperature. And you specifically mentioned the ideas of comminution and, particle size reduction and even nanograins. But you didn't, call out specifically anything connected to shear fabric development. Do you suppose that's a longer term process and doesn't really apply to the timescales that you're talking about, Stefano?
So shear fabric evolution is, I can go back to a slide that's probably partially answering to your point. So the classic, so one of the ways in which we can see fabric evolution from continuous measurement is that actually there is a continuous process of shortening, which is probably due to loss of porosity, increase of strain localization. And on top of this, there are several works from Pozzi, for example, or Smith, in which if you really stop the experiment in several points here, and you run microstructural analysis, you can see that actually localization takes some time, even with slip rates when slip rates are so high. So it's not really an instantaneous process. And typically it happens right after this stage one in gouges. It's marked by this slip hardening stage, and we have a sharp, it takes some slip, in fact, it takes some mechanical energy to undergo localization here. But it's also happening towards the tail of towards the end of the experiment, because occasionally you could also see that also again, thanks to microstructural analysis, for example, stop here, here, and here, you could see that away from the principal slip zone, actually the grain size reduction is occurring, also slightly in what can be considered as an off-fault kind of damage during the experiment, even if it's not really off-fault, it's still within the fault core, just a few microns away from the principal slip zone. And of course, there could be several techniques that help in estimating this energy term. I'm thinking about, for example, the analysis, the particle size distribution analysis that were so popular in the around 2005 and 2006 to estimate the so-called surface energy, for example. And yeah, so I think there are several evidences pointing to this.
Okay, yeah, thank you very much. Eugenio, please go ahead.
Thanks a lot. Thanks a lot, Stefano, for a very nice talk and presentation. And congratulations to you and co-authors. Do you have any idea of the thickness of the volume in which you have such very high temperatures, both in rocks or in gouge? Is it the entire volume, or just small, much smaller volumes?
We have we tried only in 2 or 3 maybe experiments to include more fibers in several positions. So one very close to the shearing surface and one a few millimeters away. And we could really see that actually the heat was localized. And this is typically the case also, for example, in the data from literature that I showed, even if it's on a different type of rock, and if it was, even if it's associated to melting of rocks, we could see that the further is your measuring point, the smaller the temperature anomaly becomes. So it's really heat production is very localized, but then with time it's basically smoothing down and diffusing away from the localization area. Yeah, I think so. It's the heat source is actually very thin. So in many modeling papers, they assume 100 micron wide principal slip zone, for example. But then with time, it could be that also this temperature anomaly is actually diffusing away. And so larger and larger volumes of near principles of rocks next to the principal slip zone are actually involved by this temperature anomaly.
Thank you.
Very nice points, yeah. And while Nicholas Brantut is getting ready to ask a question, I will re-invite people to join into the discussion. Raise your hand, join the discussion. Nicholas.
Hello. You have a plot where you show the shear stress evolution as a function of temperature or slip or something like this with different colors. Maybe if you can go back to this. It looks like, yeah, slide 50, yeah. It looks like most of the weakening is achieved when you get to 400 degrees C or so in the gauge experiments. Does that imply, well, I don't have the answer to this, but it's, so if you were to do an experiment where you start the experiments at 400 degrees or 420 degrees, do you expect the thing to be weak to start with?
It could be weak a bit weaker to start with, and I think there are a couple of options. So if there is really a temperature threshold, it could be that we need a smaller temperature increase to activate some sort of processes that activate at, I don't know, let's say at 800 Celsius. So maybe if we are a bit closer with the starting temperature, we could see that those processes are promoted, and probably weakening could be promoted a bit. But at the same time, if the material is already very weak, and we are not fast enough, so slip rate is not fast enough, maybe we could achieve some sort of equilibrium and have a small temperature increase because the material is already quite weak. So it's always a balance between the weakness of the material and how fast it's actually slipping, to have a heat source high enough to trigger some eventual weakened thermal induced process.
But yeah, sorry. I guess what I mean is that if you plot shear stress versus temperature and you tell us that it's temperature weakening, then it means that there's a one-way relationship between, if I know the temperature, then I know the stress. So let's take a piece of carbonate gouge at 420 degrees. Should the shear stress be 4 MPa at the normal stress, regardless of the speed or whatever? I mean, if you speed it up and if it heats up even more, yeah, of course, but imagine doing a quasi-static test, like 10-6 strain rate or something like this. Is it the expectation that it's really purely thermal, or is it there's something else that we're not capturing by just measuring temperature?
I think it's always a combination of slip rate and temperature. But to fully uncouple the problem, we should be able to run an experiment in which the two are imposed separately. So something on the lines of NODA 2011 would be, I think it would be the optimal case in which you can impose each of them separately as an initial condition of the experiment, and then observe the interaction between the two in controlling the shear stress. Because, for example, in superplasticity, you need actually both. You need extreme temperatures, but also extremely high strain rates. For example, if we think about nanograins and viscous creep processes.
Okay, thanks.
Thanks.
Other points people would like to raise, questions? You know, Stefano, I remember a few years ago, and I don't remember the first author's name. So there were some clever experiments done along the lines that you're talking about, where there were different heat transfer loading platen, different loading platens with different heat capacity used, and it was a paper that Andre Niemeyer was involved in, but I don't remember who else it was. It was Shiva
The
experiment.
first author is Yao.
Yao, yeah.
Lu.
Yao Lu in fault gouges from unnatural fault gouges.
Yeah, it seems like it would be an interesting thing to, combine with what you're doing, because it helps you, disconnect temperature and slip rate a little bit.
Just the roles of heat diffusion on the sample holder.
Mm-hmm. Right.
Yeah, based on that paper, we decided to develop this sample holder on a titanium alloy. Actually, Chris Arbor did it, in fact, and we tested it later in our lab. So the idea was to use a metal with a sufficiently low thermal conduction, diffusivity actually, that it as similar as we could to natural rocks, which are very insulating in terms of temperature.
Mm-hmm.
And so, yeah, with this material is a titanium, aluminum, vanadium alloy, is as similar as we could, I think, to the thermal properties of rocks.
Mm-hmm. Yeah, nice, thank you. Other points that people would like to bring up?
I don't know. This is Toshi Shimamoto from Japan. I
Please
don't know
go.
if there is the raise hand button. But hello, everyone. May I ask a question?
Yes,
Can I?
sure. Yes,
Yeah.
Yeah.
Good.
Yeah, thank you for very interesting talk. And I have two questions about the gauge temperature. And
Yes.
I think to measure the gauge temperature, you have to measure from a stationary block side.
Yes.
However, the slip zone often develop at the interface between rotary sample and gauge interface, close to that side. So what you can measure is from opposite side of the slipping zone. So which portion of temperature do you think you measured in the gauge? That's one question. And the other question is that the gauge temperature really depends on how thick is the slipping zone. So in your calculation, the what thickness of slip zone did you assume? So
Okay.
those two questions, yes.
Thank you. And maybe I can just enlarge this if I can. No, never mind. So in this, so the first point about the localization, in fact, is true. The localization in general is a bit asymmetric in gauge experiments, meaning that we've seen how typically they localize either next to the stationary or to the rotary side, depending on several things. And one is a very kind of technical or practical thing. For example, we've seen that if we screw the Teflon rings to the rotary side, and the gauge is basically spinning together with the Teflon rings, we can localize on the opposite boundary. So we can localize on the interface between the gauge and the stationary side. So very close to the optical fibers on the stationary side. Is this some sort of trick we used in this case to have to ensure the localization occurred? Because in fact, I ran several models in which I changed the position of the heat source across the gauge layer. And it's true. I mean, even if for example, the maximum localization here was set on the opposite side. So if localization occurred between the opposite, so the rotary and the gauge layer, in fact, the temperature measured by the fiber would be almost blind because temperatures are still measurable above 400 C. And so by the time the temperature is diffusing across the gauge layer, we had a low temperature anomaly, and the shape was different, was more smooth compared to the actual measurement we have. And so in this case, we assessed this point by forcing localization where we wanted, so next to the fiber. And
Sorry.
yeah.
I couldn't hear your answer very clearly, and also my English capability was not that good. And so I think were you saying that by changing the surface roughness, you can have some control. So that if you make the stationary side smoother, and you may be able to have located slipping zone on the stationary side.
Actually,
So is that what you said?
the way to control this was to fix the Teflon to the rotary side. So if you fix the Teflon rings, the confining rings.
But if slipping zone is on the rotary side, then what you measure may be lower than the real temperature in the slipping zone.
This is true, but in our case, the Teflon, which is the confinement of the gauge, was fixed with a screw to the rotary sample. And so when the rotary sample is rotating, the localization is happening on the opposite side towards the stationary side. So it's a way we found to force localization in front of the optical fiber.
So in your experiments, in most cases, slipping zone is on the stationary side.
Yes.
Oh,
Yes, basically in all cases.
so you made the stationary side, surface of the stationary side smoother
No,
than
no,
the rotary side.
the roughness is totally identical between the two surfaces. The trick was okay. The trick was fixing the confining. Can you see the confining rings? This is the Teflon, right? Can you see them on the screen? And I think it's a sort of drag effect due to the dragging, like pulling effect of the Teflon rings on the edges of the sample of the gouge layer. So if this thing is rotating and the gouge is sitting in here and compressed, sandwiched with this other sample holder, when this sample holder rotates against this other one, we localized on this side, very close to the, it's not a, it could be also a matter of roughness, but actually roughness was identical between the two. It's just a matter of how the Teflon rings were fixed and where they were fixed. We can, yeah, well, I don't know if I was clear.
Toshi, do you want to follow up? You certainly were clear for me, Stefano, but I don't know. Toshi also asked Stefano about
Yeah, the second point,
thickness
right?
of the zone, yeah.
So the second point about the shape in the models, in the numerical models, we use an end member, some sort of an end member case for the distribution of strain across the gouge, which is totally identical as in rocks, as a Dirac delta. So basically, we have one point in which we have all our maximum of shear strain rate. But it was running additional tests by choosing a Gaussian function with a 100 micron width. And this wasn't really affecting much the moderate temperature on the fiber position, let's say, on the temperature model node coinciding with the optical fiber. And yeah, I agree with you that this could be one way to decrease a bit more the temperature in the model in correspondence to the late stage of the experiment here. But I tried to decrease and match the temperatures by using an extremely large, thick principal slip zone, so an extremely wide Gaussian function, and I couldn't really match it. But I think this could be a very nice material to place also in the supplementary materials of the paper. In fact, to strengthen the point you made.
Well, thank you very much. Thank you.